Okay, so you had now the non-dimensional functions that we're talking about, non-dimensional dependent variables and then non-dimensional independent variables. So there were still a lot of independent variables. There were 4 of them, right? So we still look like this. Remember, these are Li. Just email me or really ask me a question if you are really concerned about what happened to the D and Q's or things like that in there. I don't think it really matters. Okay, so right now it's 4. It's a function of 4 variables. You can't even visualize that because it's in 4D space, right? This is a space sitting in 5 dimensions. So there's no help there at all. But one thing we know is that for pumps, usually we're operating at really fast regimes, right? Laminar pumps aren't really a big thing. We just know that this variable is going really, really large. So because of that, if you think about this sort of blade impeller going through fluid, some of the same rules apply, that each impeller is a surface in a flow field, so the Reynolds number dependencies can still work on that. But there's even just so much stuff. I mean, if it's going really fast, there's clearly turbulence. There's 3D effects that happen, meaning there's like vortices happening in 3 dimensions that are taking energy away. So it's hard to rationalize. You just know that they're operating at pretty high values. But you can just do the experiments on these things as well, or rationalize it through the Reynolds number on a flat plate if you look at the impellers. But sort of they all kind of look like something like this, where non-dimensional CP, non-dimensional head rides, and then efficiency. Okay, they all just look like a line. And this would be for varying this, varying roughness, and then varying Reynolds at high Reynolds. So this is a high Reynolds, not a laminar pump, right? So this is large. But they look like a line for this one, and this one from the experiments. You can actually argument that I found some arguments that kind of show that they would have to be the case that way, but I just think if you just did these experiments and saw this plot right here, that's it, right? Now shift that into the math, and then you go, okay, well, if those things are all constant, right? If they're just constant values, it would mean that right? That my non-dimensional function with respect to this value is 0. Same would go for this, right? If you see that plot in your head, it doesn't depend on non-dimensional roughness, right? And it didn't depend either on, right? Those plots are telling you this. What does that mean? That means that really the non-dimensional function, right, it's just a function of this. Right? In fact, all of them are 1, 2, and 3. All the functions that we wrote. So I'll leave a little I here, and I will go from 1, 2, and 3. This didn't matter. This didn't matter. This didn't matter graphically. And from experiment, all that ended up mattering was this input right here. Right? That was the axis on the x that mattered and changed all the rest. So now that thing got its own name as well. So this CQ you'll see sometimes in pump graphs. This is called a flow. So CQ is a flow coefficient. It's the non-dimensional independent variable for your pump design. That's what you care about when you're tracking, and that's what your graphs are based off of. Really, we're really just making a whole non-dimensional pump system head. And the purpose of that is you'll see to then compare operating points. What if I use the same pump, but I use a different angular velocity omega? What if I use the same pump at the constant omega, but use different diameter design for the pump? You could get the relationship based on these things. So that idea has extremely far-reaching implications, I say. Because, right, you have this CH, and then we had all the analysis just to get here. Head rise coefficient, a function whose only input really is this, power, a function whose input really owns this, function really puts only in this. So this comes down to then engineers go, aha, well then. Now what happens then if I have if I have two instances of a pump, but I have, let's say 1, 2. What if my flow coefficients equate? So the input equates. Let me redo it again, right? So for two different pumps, what if I keep this constant? The input. Well, it's not hard to see that if the input is the same, then the output have to be the same because it was the same function. Okay? So you can think of this as okay? This is what the CQ is being equal to. I just rewrote them by definition, but sometimes it's easier to think of them as input outputs. So if I keep the inputs the same, that means the outputs have to be exactly the same as well, right? If that's the case, well, that's this idea that if the inputs are the same, you get the output the same. So what does this mean? It says if you get 3 things for free. Subscript 1 for pump 2, subscript 2 for pump 2 as well. So if my input of those phi functions are the same, that would mean that the outputs are identical for 2 different pumps. Remember, this involved the Q, the omega, and the W, right? So that's the important comparisons that we have for these, right? And you can do the algebra here, and then there's 2 different cases to consider for how you would keep this thing, right? Keeping these things exactly the same. So here's the one case, right? So let's say for pump 1, the diameters are equivalent. So I'm comparing 2 pumps. They're just going to change its speed. Since they're the same pump with the same diameter, these things are going to be exactly the same. If this is the case, you could get these relationships. These are the similarity laws, given the diameters are exactly the same. 1 is the ratio of flow rates. Then you have head rise of the pumps related to and last you have boom. If this is true, this is then how you would compare the 2 pump designs that you have. So, right, so say I have the exact the same pump, I'm just going to change different speeds. So, again, I always have to reiterate, like, how on earth, how would you use these equations, right? If you're just going to use 1, you have to provide 3. You have to provide 3 of the variables to solve for the 4th, right? Because there are 4 unknowns in this equation. So I need to turn to 1 equation, 1 unknown. So these are the same. I would need to know the first state. You would also need to know then the flow rate for the first state. Let's say it's there. And you would need to know this. So I increase it to a new, so let's say I know the initial speed, I know the initial flow rate, I know the initial, and I'm considering what if I go faster? So I know this. Then you could solve for the flow rate to compare your pump. Same process through these things as well, right? So the check marks meaning if I'm going to compare, right? So let's say if these are the same, the idea is you have to then ask what's the resulting flow rate? And that's how you're going to use these. Or what's the resulting head rise? So right? If I have the exact same diameter and I increase or decrease omega, that's the thing you're going to vary. You have to know everything at the first pump state you're comparing at. Or you could use two of these equations and two unknowns. It's still tricky, right? Then you need exercises, I think, on actually just formulating that in your head to know what's solvable. Right? So there's more, and I actually have an extra credit because, or you just look them up. It's not hard to do these things, but say I run at the same speed now. Two pumps running at the exact same angular speed, and I compare them the diameters. What does that look like? Well, that's extra credit. So actually go through that and look at what the implications of equating all those non-dimensional things, right? So then what happens? Write it out, at least we do. Okay, so these are exactly the same. What does it mean then? Just rewrite these, given that, because that will eliminate that out of these equations, and you can get to references of diameters and things, right? So if these are the same, but I look at new diameters or change, find the similarity laws, and they're just based on rewriting these. They're just based on rewriting these dependent variables. And this is all, again, based on the fact that if I kept the inputs the same, then the outputs had to be the same for these non-dimensional variables. So it's ways to compare two pumps. So the idea is, I'll take, let's say, two pumps. Let's do the first case that I have. Okay, two diameters the same, two pumps, I'm going to change the omegas on them. Let's consider then head rise. Well, here's my similarity law for the head rise, right? I have to know everything about state one or one of them to compare the rest, right? So I know this one, I know the state one on here, and I even know what I increase the velocity to. So that allows me to solve for this. So that would mean that I can then compare the actual head rise for this, because what does it mean? It's a scaled version of this first pump, and then what's the conversion factor? Right, so it's three equations and one unknown for these types of things. You just have to keep in mind what you kept constant and what you're changing. So for the head rise in comparison, if I have the same diameter, if I have the exact same diameter, and I increase the angular velocity, it's a scaled up version of the first pump. Okay? More so, it's actually important on how different these things are. Right? So what's more important, I think, is just to compare what is the ratio then of this change. So, right, you can see how for something like this, for this case, right, you could just look at then the ratio of your angular speeds. Right? If I drastically decrease the velocity on the pump, that means this number is just actually nothing, so I get no head rise for the same pump with the same diameter. Right? If I have it like much, much greater than 1, if I really ramp up the angular velocity on it, you can see this is blowing up, becoming a huge number, so they just get way more head rise to a certain degree. These assumptions break down eventually. The more important thing is just like if it's just like a little bit more, a little bit less. Let's say, right, what if this was equal to 4? So increasing the velocity of a same diameter pump by 4, this would be the same as W2 is 4 times as much as omega 1. Omega 2 is equal to 4 times as much as omega 1. I've increased the speed of my pump by 4 times. What that means in velocity of your head rise is that would mean that your head rise increased by 4 squared. So much more head rise for just increasing this angular velocity. And you can just do tons of them, right? You can just there's all these similarity laws, and you can just compare an infinite amount of cases in your head. I cannot list every case that you could write down for these similarity laws, but just know they're there. Oh yeah, extra credit. Actually, this is fun. express the efficiency actually as a function only of these. Okay, so what is the, right, you can actually express efficiency in terms of CH, CP, and CQ, meaning you have no references to D, omega, anything. It's just these non-dimensional things, right? So the hint is it actually looks like. It's power law combination of all these things. But it's an interesting exercise just to get it through just like non-dimensionalizing and combining all those variables.